Hello, everyone. Maybe we can give another minute or two for people to start joining in, but just wanted to say thank you so much for joining us today with Sofar and MTS. Ciara Dorsay is going to be presenting on aerial deployment of spotters during the 2022 and 2023 hurricane seasons. She is a data analyst and boat operations team member at Sofar Ocean, and I'm really looking forward to hearing what she has to offer for us today. And finally, one reminder is if you do have questions, save them for the end and remember to type them out, as you will not be able to unmute yourself and speak on them. So let's just wait until 11 or 2:32 and then Ciara can get started. All right, Ciara, you ready?
Yep. Yeah, thank you so much for the introduction, Rebecca. Good afternoon, everyone. Thank you for taking the time today to come and listen to this talk. I hope it's really interesting. And if you have any questions, looking forward to answering them at the end. So let's go ahead and get started. Here's a quick outline of what I'll be discussing today. First, I'll be giving an introduction about our weather sensing platform, also called Spotter, as well as the program and the project that is funding the work as part of this, this work. I'll also be giving a little overview about the process of organizing spotters, so preparing it for the deployments out of airplanes. I'll then talk about the performance and observations collected by our devices during the major hurricanes that we responded to in 2022 and 2023. I'll then give a little bit of an overview about some of the work that our collaborators are doing and other downstream applications of our data. I'll then talk a little bit about the future work that we have planned for our final year of the project, which is 2024, and wrap up with some conclusions. First, I want to talk about the National Oceanographic Partnership Program, or NOPP. This is a program that facilitates partnerships between private industry, academia, and different federal agencies like USGS and NOAA. Historically, there have been a lot of barriers to these cross-sectoral partnerships and the work that is possible between these agencies. And so this program really allows quick advancement in ocean research through these partnerships. Within the program, there are a number of specific projects, and the project I'll be discussing today is the NOPP Hurricane Coastal Impacts Project, or NHCI, and each of these projects have their own objectives. The objective for this particular project is to specifically improve predictions of continental US landfalling hurricane coastal impacts via both observational and numerical approaches, which includes models. And so again, this project is valid for the years 2021 to 2024. And within the project, there are a number of subcomponents which are called tasks in the framework of NOPP. So I'll talk a little bit more about those tasks. Within this particular project, there are 5 total tasks. Sofar is only involved in task 3, which involves collecting in situ observations of waves and of water levels. And these observations are to be used for model validation and assimilation. Some of our partners as this project include the Applied Physics Laboratory at the University of Washington, NOAA, and Sears in Colorado. There are actually 2 subcomponents of this task, so task 3A and task 3B. Task 3A covers the aerial deployment of spotters or devices in general, and task 3B includes the moored deployments, which are used for observations of water levels. The scope of this presentation today is only to cover the aerial deployments, but if you have any questions about the moored units, I'm happy to talk about that. Next, I want to talk a little bit about our platform, which is called Spotter again. So I want to remind you of the project requirements. So again, we are trying to collect in situ observations of landfalling hurricanes. And as far as the project, this is defined as being done via opportunistic rapid response deployments. And what does this mean? So as part of these deployments, teams at Sofar and with our other partners, we are continuously, during the hurricane season, monitoring hurricanes and determining whether or not they're expected to make landfall. And within about 1 to 2 days of landfall, we trigger these aerial missions that deploy the devices ahead of these hurricanes in order to attempt to place the units in optimal locations for sampling areas of interest of these storms. So what's notable about Spotter, they're easy to deploy. As you can see, there's someone in the figure on the lower right-hand side deploying one of these off of a large vessel. And we actually deploy these devices as part of what we call our global sensing network, which is comprised of about 500 devices. And these devices can constantly sample conditions in the different ocean basins, and their observations are assimilated into our operational wave model. The spotter is 15 inches in diameter and 12 pounds heavy, and they have a variety of air sea sensing capabilities. So on board, we have a barometer, a sea surface temperature sensor, and they also collect and transmit observations of bulk wave parameters and spectral observations. As you can see, there are a number of solar panels around the hull. So that makes the unit solar paneled, and so they are able to transmit for extended periods of time. They're also GPS enabled, so we're able to track them as they are sampling these storms. They're also manufactured at scale, so rather than having to spend significant amounts of time creating these customized devices for this application, we already have the resources and the processes in place to quickly spin up the assembly of these units for deployment. As far as data access, the units for this particular project have observations which are available hourly, but depending on the capability of the different spotters, we do have some that can transmit via cellular. These, the frequency can be increased. And our collaborators are able to directly query these observations via our API. Next, I'm going to talk a little bit about the process of ruggedizing spotter. So as you saw on the slide before, these devices are able to be deployed off of these large vessels. However, given the altitudes and the speeds at which planes fly, we anticipated needing modifications to prepare devices for aerial deployments. One thing to keep in mind, parachutes are logistically and physically complex, and so we really wanted to avoid having to integrate these into our deployments. So we ended up conducting initial tests with no modifications at all. And so in the video on the bottom left, you can see one of our initial tests offshore of California. There's a screenshot in the middle. We ended up attaching GoPros to many of our devices to be able to look at the video and assess how the units were landing in the water and get some information about the different failure modes that we were seeing. And so some of those modes included cracked hulls and separated cables. You can see that in the figure on the right-hand side. One thing that we did notice is that spotters that landed upright did exhibit higher survival rates. And so the results from these tests really motivated the development of a structure which could control the orientation of spotters landing after these deployments. Here's a quick timeline of the modification structure development. So the testing initially began in spring of 2022. And so here you can see the devices being deployed with no modification structure at all. By mid-2022, we had arrived at some initial form factor of this stabilizer. As you can see, it's made of cardboard. And this was chosen because cardboard is biodegradable, light, easy to transport. And then by mid-August, we had arrived at a final form factor, which included some minor modifications and securing of internal cables and things like that. And then by late September, we had our first operational deployment, and this was in response to Hurricane Ian. One thing you'll notice when you look at this timeline is that there's only about 6 months between when testing began and our first operational deployment. And so in the world of hardware, this is an incredibly rapid turnaround, and this was truly enabled by the partnerships through NOPP and internal hardware expertise that we have here at Sofar. Next, I'm going to discuss a little bit more these specific hurricanes that we responded to in 2022 and 2023. So in 2022, the major hurricane that we responded to was Hurricane Ian. This particular storm impacted primarily the Florida Gulf Coast, though it did end up making landfall again further along in the southeastern US. It made landfall in September of last year, and at the time that it made landfall, it was a Category 4 hurricane. However, at one point it was a Category 5. On the left, you can see that it caused significant infrastructure damage. This is offshore of the Fort Myers region in Florida, where one of the causeways completely eroded during the storm. As far as the deployments themselves, on the right, you can see the flight path that the Naval Research Laboratory plane took in deploying our instruments, and a clip of them actually being deployed. You can also see several smaller yellow pentagons, which indicate some buoys that were actually preemptively deployed by vessels ahead of this season. And so only 10 were aerially deployed as part of this mission. Along with spotters, there were also 5 microswif buoys, which were developed by the University of Washington. There are also 5 A-size directional wave spectrodrifters, which were developed by the Lagrangian Drifter Laboratory at Scripps. As far as selecting drop locations, we really wanted to target the most intense storm conditions and offshore of any coastal features of interest. So for the other partners on the project, this included sand dunes, areas of significant infrastructure, and things like that. And we also had to balance with other modeling team needs as far as validation goals and simulation efforts. As far as the performance, out of the 10 units that were deployed, the majority of the units were healthy and captured really notable observations, some very close to the storm's eye. On the right, you can see a time series of significant wave height at the top, sea surface temperature in the middle, and barometric pressure on the bottom, associated with the spotter in the lower left-hand figure. Over the course of about 1.5 hours, we saw some really dramatic changes. So there was an about 10-meter change in significant wave height observed by this unit, a change in 2 degrees Celsius of the sea surface temperatures at that location, and 70 millibars of a change in atmospheric pressure, which are very large magnitudes in such a short period of time, really show how dramatic these changes can be as the eye of the storm passes over these regions. Also, one thing to know about the sea surface temperature is that this drop is actually associated with the vertical mixing in the ocean as the storm passes over. One thing to note is that all of these surviving units as part of this mission were actually transitioned to our global sensing network, where these observations continue to contribute to our wave model forecasts. Next, I'm going to talk a little about the 2023 hurricane season, which just wrapped up. The 2 major storms that we responded to were Hurricane Idalia and Hurricane Lee. As far as Hurricane Idalia, this storm primarily impacted the Florida Big Bend region. It made landfall in August of this year, and at the time, the landfall was a Category 3 hurricane, though it was a Category 4 at some point during its development. As far as Hurricane Lee, it actually did not impact the continental US directly, mostly Nova Scotia, but parts of the northeastern United States did feel some of its impact. It made landfall in September this year, and at one point it was a Category 5 hurricane. On the right, you can see an animation of GOES-16 satellite imagery overlaid over spotter positions and their historic tracks in green, and the spotters are the yellow pentagons. You can see the storm's eye track in red with the waypoints. And so 10 spotters were deployed as part of this particular mission. As you can see, they captured observations very close to the eye of the storm and throughout different quadrants of this hurricane. As far as the performance, we actually experienced a 100% survival rate with all of the deployments that happened as part of this particular mission. Again, several of the units collected measurements very close to the storm's eye, and you can see a time series from one of the units that actually was very close to the eye on the right. Again, we see time series for significant wave height in the top figure, sea surface temperature in the middle, and atmospheric pressure in the bottom. Moving on to Hurricane Lee, we actually only deployed 3 spotters as part of this particular mission. The reason being was that after following predictions of its track, it was not expected to be a landfalling hurricane, and it did not end up making landfall in the continental US. However, given how rapidly it was intensifying and the scale of this particular storm, we decided to respond to it anyways. We ended up deploying these units very close to the US coastline, so none of these particular airdrop spotters collected any notable observations of the storm itself. However, one thing to note is that on the right, you can see there are obviously a number of spotters that are present throughout the storm, and those are part of our persistent network. So you're probably wondering, what's the point of all these observations? I spent a lot of time talking about the particular storms and all of these observations that were made. And it's truly to, these observations are used to validate models and analyze air-sea interactions. An example of some of this work is one of our collaborators at the University of Washington recently published a work called the Saturation of Ocean Surface Wave Slopes Observed During Hurricanes. And the content of this work focused on the fact that parameterizations of deep water wave breaking processes rely really heavily on wave slope. And so these accurate parameterizations can impact our predictions of maximum wave heights in the wave models that are used for some of these storms. And how spotter observations were used is that, again, I mentioned that spotters are able to produce spectral observations of waves. And so those particular observations were used to create estimations of wind stress in these comparisons. In the figure on the upper right, you can see the spotter observations that were used. Again, these are the yellow pentagons. You can also see the spotter track of Hurricane Ian in this particular case, and the position of the spotter that was used in the inset in the lower left-hand side of that figure. There are also some regions shaded in different colors of different tones of gray. And so these tones of gray are output from a regional tropical storm model called COMS-TC, and we're used to compare and validate this particular model. In the bottom is work from another one of our collaborators at USGS, and here this is a comparison between spotter observations at a location during Hurricane Idalia in blue, and output from another model called the Coupled Ocean Atmosphere Wave Sediment Transport Model. And as you can see, there's quite a disparity between the peak significant wave height measured by spotter versus coast in this case. Without these in situ observations, we would not be able to assess the accuracy of these models, and so spotters can really be used to improve the accuracy of these models going forward. There have been a couple other downstream applications of spotter data in the last few seasons. So this past year, our observations were integrated into USGS's Flood Event Viewer. The Flood Event Viewer is a platform that's published by USGS, and it's a really great resource for different agencies, individuals, researchers, and it allows one to quickly and easily co-locate different measurements. So we were able to have our observations from spotter integrated into this platform, and those can be co-located with barometric pressure sensors, water level sensors, tidal gauges, and rain gauges. Finally, there's the National Mesonet Program, which we also recently became integrated into. This is another partnership between government, academia, private industries, and the goal of this program is to really supplement federal weather data sources with information that is expensive and difficult to maintain from a federal agency perspective. And so how these observations are being used is that they're also used to, they're being assimilated and used to validate these models. They're also used in public warnings ahead of some of these storms. If a lot of this research interests you, we will be continuing to post updates in the two links in the bottom right-hand corner, and so you can continue to follow along with updates there. So I want to wrap up with some conclusions. As I discussed earlier, spotters are highly suited to this task. Given the ease of deployment associated with this platform, given that they're very light and robust, there are a number of air-sea capabilities already integrated within this platform. They've proven to be highly suited to collecting useful in situ measurements of hurricanes. The rapid response method of responding to hurricanes has also proven to be incredibly viable. As you've seen, given the three last major hurricanes that we've responded to, we were able to collect a number of measurements that were very close to the eye of the storm that can be used to validate and improve existing weather models. The collaborative partnerships as part of NOPP really enabled the successes that we've seen in the past few years. And without these partnerships, the speed and number of goals that we were able to accomplish would have not been possible. As far as future work, so the 2023 hurricane season has really come to an end. Our collaborators will continue to work with the observations that have been made by our spotters in the 2022 and 2023 seasons. As far as next year, that will be the last year of the project. We will be deploying a similar number of spotters, and we have the resources to respond to 3 landfalling hurricanes. As far as beyond, this has been a really insightful project for Sofar, and there have been a great number of successes, and we'd like to continue this kind of work moving forward. So we are having internal discussions about what we can do to continue to make observations of hurricanes. That's really all for me. I do want to extend acknowledgements to the rest of our collaborators within the NHCI project, and another thank you to all of the others at Sofar Ocean who helped make all of these successes possible. I also want to extend a special thank you to the Naval Research Laboratory's VX-1 Squadron, who were the individuals who actually deployed our devices during the hurricanes in the last 2 years. If you have any questions, let me know, and you can find more at the NHCI webpage at the bottom there. Thanks.
Thank you, Ciara. That was great and super insightful. We have one question coming from Leslie. She wanted to know that she asked, I know you mentioned aerial deployment. Have you ever tried drone yet?
No, we have not experimented with deploying by drones.
Great. Are there any other questions? I have one question. You mentioned something about data assimilation and how you're using those observations to assimilate back into the model. Could you maybe elaborate a little bit more on that?
Sure. I guess I can speak more to the assimilation that we're doing internally. So our collaborators are assimilating our observations into the models that they're running. But here so far we have an operational wave model. Again, we have this global network, about 500 devices, and they are hourly transmitting observations of different bulk parameters and spectral wave observations. And those are assimilated, and those are used to basically like improve, they pull our model to reality, because a model is basically like a set of math equations that are running all the time and solving for conditions at a given point in time and space. And by providing these in situ observations, we're able to like kind of calibrate in a way every few hours or every hour.
Great. Thank you, Ciara. We have another question from Seibert Murphy. He's asking, or she or they is asking if you can add sensors to Spotter.
This honestly might be a better question for you, Rebecca. I guess Spotter in its base form, at this point, no, but we are developing a technology here at Sofar called Bristlemouth, which can be used to integrate sensors, but I'll let you talk about that a little bit more.
Yeah, thank you, Saber, for that question. So we are developing an open standard. It's called Bristlemouth. Please visit bristlemouth.org to learn more, but the purpose of it is to enable ocean technology to be kind of developed at faster rates, by creating an open standard hardware, kind of like a USB key, but for the ocean. So even though Spotter is not there yet, we are working with Bristlemouth to do that. And then, okay, Ciara, here's one for you from Murugesh. How are the sensors are the sensors protected from high impact while aerial deployment? So how are they now ruggedized?
I guess the spotter hull in itself is already incredibly robust. We've done a lot of testing here at the office and some other field testing nearby to make sure that these hulls are, and the sensors within them are like sufficiently resistant to high impact forces, again, because of the deployments that we regularly do. Most of the internal hardware is contained within this like hard plastic hull, and so they're not really exposed to direct impacts. Yeah, I hope that answers your question.
Great. And then we have a couple more. Okay, what would it take, question from Chidong, what would it take for the operational forecast centers to receive your data in real time?
They already do. We have an API, and so it's really easy for our collaborators and for other agencies, once we work them to make sure that our data is up to their standards, that most companies have infrastructure to like quickly tap into this API and then immediately start getting live updates from our network and any other of the devices that they have access to.
Great. Yeah, that's one of our main, I guess, offerings. Okay, two more, Ciara, you got this. Are you considering hydrophones as an addition?
We were for a while, but again, with Bristlemouth, we're really trying to put these capabilities of customized sensors into the hands of the users rather than trying to account for all of the different possibilities on our end, which can be incredibly time consuming. And, this allows the user to really integrate like whatever they want.
Yep. If you are interested in hydrophones, please check out Bristlemouth. We already have some early access customers actually integrating our Bristlemouth technology with hydrophones. Okay, last question from Lynn. Why is the program ending next year? Will this project have all the data needed to answer questions surrounding the project needs?
I think government funding is usually pretty finite. You're given several years and X amount of funding to accomplish the task at hand. So, that's the case for this project as well. But, the government is consistently putting out different grant offerings that we can apply to that will work is very similar to, or we have program managers that we work with that really enable us to find ways to continue making powerful observations and continue this kind of work. So we'll see what the future holds.
Great. Are there any more questions? If not, I think we're just about at time. So thank you everyone for joining. And again, thank you so much, Ciara, for taking the time to be with us today. Everyone's saying thank you as well. All right, well, enjoy the rest of your afternoons and have a nice week.